Okay, great. So we'll be solving problems on stability of equilibrium. Got it? Okay. So note down on problem. You can note down this. A heavy uniform cube So note down one more. A hemisphere rests in equilibrium on a sphere of equal radius. So that the equilibrium is unstable. So that the equilibrium is unstable when the curved and unstable when the flat surface of the hemisphere So this is the problem statement. See this, a hemisphere rests in equilibrium on a sphere of equal radius. That means there is one sphere and there is one more hemisphere. So let us say this is the sphere and this is the hemisphere. Right? So the curved surface is in contact with the sphere. This is case 1. And the second case is, this is the sphere. So this is the hemisphere. Now this is case 2. So in case 1 actually this is unstable equilibrium. And this is stable equilibrium. And that's what actually he asked us to prove. Right? So the radius of both the spheres are same. That means if this is the center and this is the radius, so this is R. And similarly if this is the center and this is the radius and this is also R. And as I said earlier, so this is the straight line. So the point of contact will be exactly below the center of gravity of the top body. Right? So here in this case there is no confusion because this is equally distributed on left side and right side. Now here in this case, if you want to find out the stability of the equilibrium for this particular system, we have derived one important formula, that is cos alpha by h is greater than 1 by rho 1 plus 1 by rho 2. Then the equilibrium is stable. Equilibrium is stable. Otherwise, it is unstable. So this is cos alpha by h is less than 1 by rho 1 plus 1 by rho 2, then this is unstable. Now here actually only thing is we need to identify the rho 1, rho 2 and h and alpha values. So here actually the alpha value what we have taken in the derivation is nothing but the vertical line angle. So with respect to this line, so the body center of gravity, actually if you draw a line like this, and that's what is the angle. Now here in this case, the center of gravity and the point of contact, this is nothing but the common normal. So this is the common normal. So alpha is the angle between the vertical line and common normal. And here in this case, that angle is 0 because actually common normal and the vertical line are one and the same. So once we got the values, here actually what he has given is rho 1 is equal to rho 2 is equal to, in the case 1, rho 1 and rho 2 both are equal to r. So this is case 1. In case 2, here actually this is radius r1. Now what is the radius of curvature of the top body in contact? So at this particular contact area, what is the radius of curvature for this particular line? Here actually we know that the radius of curvature is r, but here actually this is a flat line. So what is the radius of curvature of your flat line? What is the radius of curvature of your flat line? So no, it's not 0, right? With 0 radius actually can you draw a curve? No. Then, so what is the radius of this line? It should be infinite, because any line you can draw or you can interpret as a curve. This is a straight line. Straight line is a curve with radius infinite, right? So radius of curvature infinite. That means, so look at this way. So this is actually this portion of the curve if you think of. So this is actually it's a certain radius, you can draw this curve. Now actually if you draw a line like this, so this circle, now the same portion actually, suppose if you take a length of 1 centimeter, so this is some curve, but the same length of 1 centimeter here, you don't feel like it's a curve. Suppose if you take bigger line like this portion of the line 1 centimeter, you don't even feel at all as a curve, right? If you just look at only this portion of 1 centimeter, removing the entire circle, you feel that as if like it is a straight line, right? But if you look at as a bigger picture, this is a circle of radius certain value, right? So this radius if you are increasing, then the curve is going to become as a straight line. So that means if you draw a circle with infinite radius, you are going to end up with a straight line, right? So here exactly the radius of curvature for the top body. So if you look at from the top side, right? So the radius of curvature will be, obviously this is infinite, right? So if it is infinite, then rho 1 is the top body, so this is infinite, and rho 2 is the bottom one, which is equal to r. So in case 1 and case 2, if you substitute it, so alpha is anyway 0 and h is the center of gravity, which we are going to calculate now, and then 1 by r rho 1 and 1 by rho 2. For case 1, this is 1 by r plus 1 by r, so this is going to be 2 by r. So right side part is 2 by r and the left side part is 1 by h. H we need to be calculating for this particular case, so which we are going to do it now. So you note down this. So in case 1, so 1 by h should be greater than or equal to, for stable condition, right? So we will calculate 1 by h value. So h is the center of gravity of the top body above the point of contact. So this is the center of gravity, let us say. So this is the point of contact A. I call this as G. AG is h. H is equal to AG, which is the height of the center of gravity for the top body above the point of contact. So this one for a hemisphere. So if I draw the hemisphere like this, then the center of gravity actually, so mathematically we can calculate it. For now you don't need to calculate because actually there is a separate topic dedicated to this called mechanics. So there actually we are going to deal with that. So this is at a height of 3/8 times of the radius. So this is the center of gravity from the center. So this is the center of gravity from this point, which is nothing but the center to the center of gravity height. This is at 3r/8. So this is the center of gravity. But actually in this case, the body is actually in inverted form. So it's not like this. This is actually this way. Now the center of gravity is at a height of r minus 3r/8. So this is h is equal to az equal to r minus 3r/8. So this is 5r/8. This is the h value. So 1 by h is equal to 8 by 5r and 1 by rho 1 plus 1 by rho 2 is equal to 1 by r plus 1 by r. This is equal to 2 by r. Now to compare these two, we will make common denominator. So for that actually what I can do is this I can write as 10 by 5r. So this is 10 by 5r and this is 8 by 5r. So 1 by h. So if you compare these two, 8 is less than 10. That means this is how you can write it. Rho 1 plus 1 by rho 2. So hence it is unstable. Got it? So this is straightforward and simple. So nothing complex. We are calculating 1 by rho 1 and 1 by rho 2, but identifying the 1 by rho 1 and 1 by rho 2 values is very, very crucial. And h especially. So we are tempted to find out the h value like this, but this is r minus 3r/8. So that's how actually you have to calculate the h value. By definition, the height from the point of contact to the center of gravity of the top body. So that is how you have to calculate it. So this one, when we are comparing also, don't get confused, try to make common denominator and then try to compare the denominator. So numerator. So this is 10 by 5r and that is 8 by 5r. 8 by 5r is less than 10 by 5r, hence this is unstable. So for stability, it has to be greater than. Got it? Yeah, you can note down this. And the case 2 also, it is straightforward. So one radius is this radius of curvature from the top to the contact of the surface. So this is infinite. So the right side part is 1 by rho 1 plus 1 by rho 2 for the second part, 1 by infinity plus 1 by r. So this is 1 by infinity is anyway 0. So this is 1 by r on the right side. And the left side is the center of gravity of the top body from the point of contact. This is 3r/8. Right? So one is 3r/8. And then 1 by h value. It implies 1 by h is equal to, so 8 by 3r. And that is 1 by r. So 1 by r and 8 by 3r. So multiply 3 on the top and the bottom. So 8 by 3r is greater than, case 2, 8 by 3r is greater than 3 by 3r. Common denominator. So hence this is a stable equilibrium. So this is unstable and this is stable. What do we mean by unstable and stable here? See this. If I try to push this like this a little bit, then actually there is very high possibility that this will fall down like this. But in this case, if I try to push a little like this, if I leave it, automatically it will go back to its stable condition. So this is stable equilibrium and this is unstable equilibrium. So little movement to this one will make the body under unstable condition. Got it? You can note down this. Note down one more. A body consisting of a cone and a hemisphere. A cone and a hemisphere on the same base rests on a rough horizontal table. Rests on a rough horizontal table. The hemisphere being in contact with the table. So that the greatest height of the cone so that the equilibrium may be stable. Is root 3 times the radius of the hemisphere. So this is the problem statement. Here, a body consisting of a cone and a hemisphere. That means two different bodies are there. So both are jointed together. So the same base. So that means both the bases are actually common to each other. So that's why actually it is the same base. That means, so there is one hemisphere like this and there is a cone like this. So this is how actually it is. Right? So both are sharing the same base. This is the same base. And the hemisphere is in contact with the ground. Right? So this is how actually the problem statement it was given. So being in contact with the table, show that the greatest height of the cone. So that means I'll draw a neat diagram. So this is how it is, and the height of the cone is this one. And this is the center. And this radius is R. Right? So radius is R. And this is the table. So this height is again R. So because this is the radius of the hemisphere. Now what he asked us to find out is height of the cone so that the equilibrium may be stable is root 3 times the radius of the hemisphere. Now actually the bottom body is in contact with the ground. Now this has to be under stable condition, right? This has to be under stable condition because this is under contact with the body, under contact with the table, and the radius of curvature of the bottom surface is how much? What is the radius of curvature of the bottom surface? It should be infinite, exactly, right? Because actually this is the horizontal table. And what is the radius of curvature of the top surface? What is the radius of curvature of the top surface? So top surface is this one. And this surface is having, so the radius of curvature actually we should be worrying about only at the point of contact. So that is how actually we have derived the derivation, if you notice. So we don't need to be worrying about the radius of curvature for this part or the top part or anything like that. So we have to be aware of the radius of curvature only for this particular portion where it is in contact with the ground surface, right? So that means this is the point of contact, hence actually we should be worrying about the radius of curvature for this particular portion for the top body, which is again a circle. For us it is equal to r, right? So this radius of curvature is r and this radius of curvature is infinite. So rho 1 is equal to r and rho 2 equal to infinite, right? Rho 1 equal to r and rho 2 equal to infinite. Now one more key information what we need is alpha. Anyway we know that actually this is in the common line, so the common normal is nothing but this is the common normal which is making 0 angle with the vertical line. So cos alpha is anyway 1. And the other information what we have to be worried about is the center of gravity height. So the height of the center of gravity. Above the point of contact. So this is what actually we need to be finding out. Now actually it consists of two different parts of the body. So because actually we cannot straight away find out the common center of gravity for this particular shape of volume. So because the top portion is different and bottom portion is different shape. So when we wanted to calculate the bottom part and top part together, if you want to find out the center of gravity, what we can do is, so there is one rule, like actually suppose this is having a volume of V1 and this is having a volume of V2, and the center of gravity which is at a height of, let us say, Y1, and this is having a center of gravity at a height of Y2, then the common center of gravity height from the bottom where you have taken as the reference, so this is x-axis, then actually this point is 0, 0. So x center of gravity we don't need to be worrying about because actually this is anyway on the common normal, anyway it is not needed for our calculations purpose. We need only the height of the center of gravity from the contact surface. So if you want to find out the contact surface height, so h is equal to, so V1 Y1 plus V2 Y2 divided by V1 plus V2. So this is how actually we will be finding out the center of gravity when there are multiple bodies that are involved, right? So V1 Y1 plus V2 Y2 by V1 plus V2. So this is a common formula, whatever may be the number of parts that are present, right? So this is how you will be finding out if there are V3 or V4 also, V3 Y4, V3 Y3 and V4 Y4, and in the denominator also V1 plus V2 plus V3 plus V4 it comes. So this is how you will be finding out. Now it is up to you to calculate the V1 and V2, so that you have to be aware of it. So what is the volume of the hemisphere? What is the volume of the hemisphere? So 2/3 pi r cube. So for a complete sphere it is 4/3 pi r cube. For a hemisphere it is 2/3 pi r cube. And what is the volume of the cone? One-third pi r square h, exactly. 1/3 pi r square h. Right? So one-third pi r square h. So I call this a small h, that is more convenient for me. So 1/3 pi r square h is the volume of top part. Now, so you have to be finding out the center of gravity for each and every body separately. Then only you will be able to find out the common center of gravity. So Y1 and Y2 we have to be aware of it. So what is the Y1 value? So which is the height from the ground to this particular point. So this we have already calculated in the previous problem. From top actually we have calculated to be, that is 3/8 times of the radius, and from the bottom actually you can find out, that is 5 by 8 times of the radius. So y1 is equal to 5 by 8 times of the radius. That is the y1. Now what is the center of gravity of a cone from its base? From its base. What is the center of gravity of a cone? So you try to remember it. So this is at a height of h by 4. This is the center of gravity of a cone. So from this particular surface. Now in total, this center of gravity is at a height of r plus h by 4. So that is the total height from the ground to the center of gravity of the second body. So y2 is r plus h by 4. This is y2. Got it? I'll write it here. It's not visible. y2 is equal to r plus h by 4. Now we have got all the values. So you will be able to find out the h value, and then the base formula anyway we are aware of, that is cos alpha by h is greater than 1 by rho 1 plus 1 by rho 2 for stability, for stable. So this we have to substitute it. First you note down this and try to simplify this and tell me what is the h value. So what do we mean by h should change? The h is nothing but the common body, the complete body center of gravity height from the ground. So this h actually, it won't be y1, it won't be y2, it will be somewhere in between these two. Got it, Vishal? Cone height is h by 4. So total cone height is h, and the center of gravity of this cone is at a height of h by 4. Now actually I have given clearly y2 is equal to r plus h by 4. Because this center of gravity, from here it is h by 4, from bottom it is r plus h by 4. Got it, Vishal? When we calculate the center of, so just listen, when we calculate the center of gravity, you have to take a single coordinate system. That be cautious. So see this, for this top body, the center of gravity, you might be tempted to find out from here to here, that is h by 4. But for overall system, actually we have to be fixing single coordinate system, that is this x-axis and this y-axis, and this is the reference point. So when we refer any center of gravity for each and every part of the total body, you have to refer from here only. That is the common center of, so this is the place actually where we have taken as a reference for all the independent parts. So this one is at a height of y1 and this one is at a height of from here to y2. Got it? So for every body, right, you have to calculate from here only. So h is equal to v1 y1 plus v2 y2 by v1 plus v2, and this is v1 is the bottom body, that is 2/3 pi r cube plus into y1 is 5r by 8 plus v2 is 1 by 3 pi r square h into the center of gravity is r plus h by 4 whole divided by 2 by 3 pi r cube plus 1 by 3 pi r square h. Now this simplifies to, so pi r square you can cancel out and 1 by 3 also you can cancel out. So 2r into 5r by 8 plus h into r plus h by 4 whole divided by, so 2r plus h. So this is what is left over, right? So this is the h value. If you further simplify it, five r square by 4 plus HR plus H square by 4 whole divided by 2R plus H. 5R square plus 4HR plus H square divided by 8R plus 4H. So this is H value. Now actually if you substitute 1 by H should be greater than 1 by rho 1 plus 1 by rho 2 for stable condition. 1 by rho 1 plus rho 2. So rho 2 is infinite and rho 1 is R. So this is 1 by infinite plus 1 by R. So it implies 1 by H should be greater than 1 by R, or H should be less than R. I hope you are aware of it. So when we invert the denominator to the numerator, then less than becomes greater than and greater than becomes less than. So 1 by H is greater than 1 by R, or H less than R. So H value actually we have calculated. So H value we have to put it here. Okay, you note down this. I am going to erase it. Don't get confused with this H. So this is, I call this as capital H. This H is different and the other H is different. This H is the center of gravity of the complete body from this particular point. That is capital H. And small h is the cone height. Then noted. So if you simplify this further, H should be less than R. So H is 5R square plus 4HR plus H square divided by 8R plus H should be less than R. It implies 5R square plus 4HR plus H square should be less than 8R square plus HR. Three HR plus H square should be less than 3R square. Sorry, this is 4H, right? Yeah. So this is 4HR. Yeah. Now it is cancelled. Yeah. So H square less than 3R square. So it implies H is less than root 3R. So this is the condition for stable equilibrium. Got it? So if you notice, right, so in all the problems actually we are deriving from the single fundamental equation cos alpha by H should be greater than 1 by rho 1 plus 1 by rho 2. So this is the single fundamental condition. Then rest of the thing is actually only you have to be aware of the fundamentals of calculating how we are calculating the center of gravity. So how we are calculating the height. So all those things actually you have to be aware of a little geometry, that's all. And only this is the formula. So other than this actually there is nothing more than that. Got it? So I hope you noted down. Note down one more. A heavy uniform cube, balances on the highest balances on the highest point of a sphere whose radius is r. Point of a sphere whose radius is r. If the sphere is rough enough to prevent sliding, if the sphere is rough enough to prevent sliding, and if the side of the cube is pi r by 2, is pi r by 2, show that the cube can rock, show that the cube can rock through a right angle without falling. So this is the problem statement. Now here actually what he has given is a heavy uniform cube balances on the highest point of a sphere. So first we draw one sphere like this, and then there is a cube on top of it. So this is a cube on top of it. Now this one is having a radius of r. This is the common normal. And this is the radius r, and this height is pi r by 2. Now this is being a cube. What will be the height of the center of gravity of the top body from the point of contact? What will be the height of the center of gravity from the point of contact? It should be pi r by 4. So this is at a height of, this is pi r by 4. Now actually first of all we have to be proving that this is under stable equilibrium. Now the problem statement what he asked is, so if the sphere is rough enough to prevent sliding, and if the side of the cube is pi r by 2, show that the cube can rock through a right angle without falling. Rocking meaning if you tilt like this, then how much time actually it will withstand, or actually how much distance it will withstand if you tilt like this. Now when will this fall down? So when this particular point is in contact with this part, then actually the roughness of the sphere will not prevent this from falling, right? So that means when this part actually, when you are tilting like this, if it touches somewhere here, then definitely it will fall down, and that is the condition for the fall. But before that we have to be aware of this is standing on it. So for that actually what we have to prove, that is this is under stable equilibrium. That is the first thing what you need to prove. And then if it is under stable equilibrium, then you can think of when it is going to fall down. So that is this length we need to be calculating, and this length we need to be calculating, and within that how much angle that is going to be there, that will be the angle through which it can rock without falling, right? So first we will prove that this is under stable equilibrium. For that, this radius of curvature is rho 2 is equal to r, and radius of curvature for the top one, which is nothing but rho 1 is equal to infinite. And the height of the center of gravity from the point of contact is pi r by 4. So 1 by h is equal to pi r by 4, that is 4 by pi r, that is 1 by h value, and 1 by rho 1 plus 1 by rho 2 is equal to 1 by r plus 1 by infinite. So this is 1 by r. So 4 by pi r and 1 by r. So top and bottom I will multiply with pi. Now actually if you notice denominator is pi r and the numerator is 4 and pi. So pi value is anyway 3.14. Hence this is going to be more. So 1 by h is greater than 1 by rho 1 plus 1 by rho 2. Hence this is under stable equilibrium. So this is the first part. And the second part is, so it will try to withstand till the point this corner actually is going to touch this one. Now what is this length? This length from here to here, I call this as A and this is B and this is C. So AB equal to AC equal to, so this is being the cube, this length and this length will be same. So that is pi r by 4 is this length. Now, so when it touches on this side, it will make an angle of theta, let us say, when this point is B dash. So this is making an angle of theta. Now this arc length is nothing but this length, because actually both are actually without slipping, it is trying to roll like this. Hence this length will be same. Then only actually this point will be in contact with this one. Then it is going to fall down automatically. So that time this length value pi r by 4 has to be equal to, so arc length is r theta. And this r will cancel out. It implies theta is equal to pi by 4. So on the right side, it will make an angle of pi by 4 without slipping or without falling. On the left side, it will make an angle of pi by 4 again without falling. So this is pi by 4 and this is also pi by 4. Hence, it can rock through an angle of pi by 2. Got it? Any questions on this? Okay, so this is about the statics part of this syllabus. So do you have any questions on this particular topic? On statics actually, do you have any questions? I hope you people are feeling comfortable with the statics topic now. So what is your question? Cos alpha by h is greater than 1 by r. Yeah, that you can make use. Yeah, that can also be done. So this is one way and the other way is that one, cos alpha. Yeah. Got it? So overall actually you people are comfortable with this particular topic, statics. The only thing is actually you need a little bit of geometry to understand. That is very, very crucial. And along with that, vectors is the other topic which you have to be aware of before even starting the preparation for this particular topic, right? So those topics you don't need in depth also. You have to be aware at +2 standard, whatever you have learned, that you have to be pretty comfortable. This is the requirement for this, right? So other than this, actually, if you notice, nothing great we learned. So everything is pretty straightforward and simple. We are dealing with only the force. That's all. Nothing more than that. Got it? Yeah. So with this, I am concluding this topic. So we are going to start dynamics classes from Monday onwards. If you have any questions on statics, you can let me know now. Any questions? So yeah. So great. So we can start Monday again. So catenary, actually I have solved problems, right? So I am going to give assignment on catenary. In case if you don't know any problem, actually you can ask me back. I will solve it. Fine. Okay, you tell me the problem actually which you are not able to solve. So I am going to give the solution for you. Fine.